Good afternoon, everybody. So today we're going to start out real basic, go through some of the what is temperature, define the temperature scales, and then I'm going to get into talking a little bit about thermocouples and RTDs and what they are and how they're different, kind of where they should be used, and then if you have one in your facility and you don't know what it is, we're going to go through some methods on how to identify whether it's an RTD or a thermocouple, what accuracy range it might be, those types of things. And then if there's any other things towards the end of this, feel free to jump in and plug in a question to the chat box or Q&A. So first off, real basic, what is temperature? We all know it's, hot or cold, and our reference point is 72 degrees Fahrenheit. I guess that's where most people are comfortable. So we say it's either hotter or colder than that is kind of pretty typical. Here in Minnesota today, it was 0 degrees, and we know that that was really cold. Even sadder is that was one of the warmer places in the state today.
That's winter in Minnesota for sure.
So it's just a measure of kind of the motion of the molecules and the energy they have. And if we look at some temperatures of some different things, you kind of pick your favorite off the list here. The three that are kind of most important for, at least in the metrology world that we work in, the ice point is real common, liquid nitrogen. And there's also the triple point of water, which I don't have on this list, but it's at 0.01 degrees C. Some other things, we have the different scales. And I guess if anybody's purchased a new light bulb recently, it always has a number on there like, 3000 K, and that's actually the Kelvin temperature scale. And what that is, it's a reference to an ideal black body that's heated up to a certain temperature, and the light that comes out of that is at that temperature in Kelvin. So a light bulb that's like 3000 Kelvin kind of has that nice warm kind of yellowish glow to it, and if it's a 5,000 or 6,000, that's kind of sunlight, real bright white light. And the Kelvin scale is one that we use in metrology quite a bit, as well as Celsius. Years ago, the Celsius scale used to be called centigrade. That terminology isn't used anymore because it means some different things in Spanish and French languages. So Celsius is the correct name for it. Came up with this Anders Celsius way back when, and it's just based on the freezing point of water chose that as 0 degrees C, and the boiling point of water is 100 degrees C. The Kelvin scale is an absolute scale, so the 0 point there is absolute 0, and it's a theoretical point, so which all the molecular motion stops, and they're at a kind of a 0 energy state. The Fahrenheit scale, that was developed with the 0 degree point was where fully saturated salt water will freeze, and he chose that as his 0 point. Oh, before I move on there, one note about the Fahrenheit or the Celsius and Kelvin scales is that the magnitude of each degree on those scales are equivalent. So if you move by 5 K on a temperature scale, that's the same as moving 5 degrees Celsius on the scale. It's the same amount of temperature change. So the different types of sensors that are out there, we've got liquid displacement, which would be like a, the little thermometer you use to take your temperature. When you have the flu bug going around, there's some dial thermometers that use a little bimetal coil like this one right here. And that's the kind that might be hanging on the tree in your yard. It uses a little coil of metal, and it's just two metals that are bonded together. One expands more with temperature than the other, so it causes that coil to tighten up or loosen with a change in temperature, and that in turn makes the little red needle on the dial go around and indicate a temperature. Highly inaccurate, at least when compared to some others, but it does a fairly good job with outdoor temperature. There are thermistors, which is a little kind of a solid state device. Then there's optical sensors, infrared, laser, and then that'd be the DTS or distributed temperature sensor. And then the ones that are used mostly in industry would be thermocouples and RTDs. And RTD is a resistance temperature detector, and we'll cover both of those in more detail here. Liquid displacement. Pretty limited temperature ranges. Accuracy is not that good. And when you read the dial, you can, based on how you look at it, you can get any number of different temperature indications. So a little bit of human error comes into play there. Thermistors, these are very small, typically used in, they might drive the temperature display in your car, for example. They're very good for a small temperature range. They can be pretty accurate. They do drift over time. They have some self-heating errors, so when you run a electrical current through them to measure the resistance, they can heat up a little bit and cause a reading that's higher than actual. And another big plus they have is that they're very inexpensive. It might only be, 50 cents or $1 a piece to plug that into your automotive temperature measurement system. Thermocouples, these are used in industry quite frequently. They're very durable, really low cost. The way they're made is just two dissimilar metals. So we just take two wires of different materials, hook them together, and if you run them through a temperature gradient, you're going to be able to measure a voltage. And that voltage changes with temperature. So as the temperature goes up, that voltage increases. Temperature goes down, the voltage decreases. They typically use an ice point as the basis, so they know if the junction, there's a little hot junction here at the tip of the sensor. So it's just like a zero reference between that and the tip, so we know what that. So the instrumentation knows how to measure that voltage. The other big advantage with these is that they work over a really wide temperature range. We can go down to probably liquid nitrogen on up to a couple thousand degrees Fahrenheit with a variety of types of thermocouples. Even some of the platinum tungsten rhodium ones go up to about 4200 F. That's about the highest. These are all identified with different color codes. The ones at the top here would be called base metal thermocouples. So they're a type T would be red and blue. All of the negative leads are all red, and it's just the positive lead color that changes. And each one of these has a different voltage versus temperature characteristics. And each one of them is designed for different temperature ranges. For like example, the type T is used frequently for below 0 temperatures. Type K can handle some of the higher temperatures. It works the best for higher temperatures. And all of the platinum, rhodium, or tungsten versions, those are all used for very high temperatures. You can see here just a quick graphical comparison of all the different temperature ranges and where they can be used. When thermocouples are constructed, they can be an exposed junction like I showed a couple of slides ago, where it's just some ceramic insulators and the little wires are welded together and they're just exposed to the process. Most of the time, though, to get a good long life out of these, they need to be protected. And so we use a metallic sheath and then have the conductors insulated with either fiberglass or some kind of ceramic powder. And the junctions can either be attached to this metallic sheath, so it'd be a grounded junction. Some reasons to do that would be if you want a faster time response, or if it's a real high vibration environment, having that junction welded right into the tip of the probe can add some additional durability to that part. For I guess what I see mostly is the ungrounded junction, so the junction is completely isolated from the metallic sheath, and these are typically it's done so that if you have some electrical noise in your system, might be static or stray voltage or whatever, it's not going to interfere with this thermocouple because it's electrically isolated from that environment. And just to reiterate here, very wide temperature range. I see we go down 1.2 K, so that's some special type of thermocouple. I don't recall exactly what that might be, but on up to 2300 degrees C. So really wide temperature range. These can also be made really small, so we can have a really fast response time. You could have, wires that are 0.010 of an inch diameter and have it in an exposed junction. And in an airstream, that's going to respond like in just fractions of a second. Again, really low cost and very durable. The kind of the biggest disadvantage with thermocouples is that they do drift over time, and it can be fairly significant depending on the temperature range that they're used at. Usually the higher the temperature is, the faster they're going to drift. And the other big disadvantage is with recalibration. And there's really not a good way that you can take a thermocouple and pull it out of your pipeline or tank and go take it to a lab and measure it and then bring it back and have it actually perform the same as what you just measured in the lab. The best way to do it is to measure it right in that spot where you may just pull the thermocouple out and put it in a bath of known temperature and read what it's telling you. And that's keeping all of the lead wires and everything all connected up the way they are. And that way you will, get a better idea of how accurate that thermocouple is as it's installed in that system. Long-term stability, again, they like I said, they do drift, and so that can be a little disadvantage also. Resistance temperature detectors, and I think before I dive into this, if we have any questions now, we could.
We do actually have a question, and it fits exactly with RTDs here. So I won't mention the name to protect the innocent, but their comment is our electrical engineer gets really picky about his vocabulary when talking about PT100 devices. He refuses to call them RTDs. What's this all about? So it's
there are a lot of names. So yeah, PT100 is fairly common. An RTD is a very generic term, as it shows on the slide here. They can be made from platinum wire, nickel, copper. There was years ago, there was some stuff called Belco, which I think was iron and some iron alloy, whatever, that someone made a resistance temperature detector out of. Right now, the most common, of course, is platinum wire. It's got the widest temperature range capability. It's the most stable and repeatable. There's still a few nickel and copper ones around, but those are typically in older systems, and people just haven't switched over to the new and better stuff.
So the short answer is RTDs is RTD is a generic term, resistance temperature detector. PT100 stands for platinum 100, which is just identifying the material that's used in the sensor.
And the 100 indicates that it's 100 ohms at 0 degrees C. There are other resistances that are made. One of the more common ones would be a 200 ohms at 0 degrees C, and then there's a 500, which I don't really see much of. But in some of the HVAC systems, we'll use a 1,000 ohm sensor. So if you were to measure that sensor at 0 degrees C, it's going to have 1,000 ohms of resistance.
So to be completely accurate, if you're dealing with a PT100, that's a platinum resistance detector as opposed to just a resistance temperature detector.
You're probably better off just playing along and just say PT100.
Yep, exactly.
It's a little more specific. Let's see. So was that it then? I guess
that was it.
Okay.
And again, just a reminder, if you do have any questions, go ahead and type them into the chat box or the Q&A section kind of as we go, and we'll go ahead and try to get you an answer.
Yeah. Got one more thing I wanted to mention on this slide. The couple very common styles of platinum resistance thermometers, PRT, which is another term. This would be a wire wound or a coil style, and this happens to show a dual sensing element. So just this little cutaway here shows the coils of platinum wire inside this ceramic mandrel. These are typically about a 1/16 of an inch diameter across here. So you can imagine it's all very tiny stuff, and all the assembly is done under a microscope. The wires here, 7/10 thousandths of an inch diameter. And then the lead wires out the back are some of the better ones will have like a platinum rhodium alloy, so they're a little bit stronger than like pure platinum, and those are anywhere from maybe 10 to 15 thousandths diameter. The thin film sensors, and this one is shown highly magnified. It's actually maybe a 1/16 of an inch wide here at most, and then the length. Most of the length here is just to be able to attach lead wires to it. The actual platinum film is this little gray spot here, and I don't know if this photo is good enough, but you can kind of see where there's a path that's, they just deposit a layer and then they use a little laser to cut away the platinum that they don't need to make a 100 ohm path out of it over the little ceramic substrate. So they can be made very small, and if they're put together correctly and packaged, they can be a lot more durable than the wire wound styles. You know, you can imagine these coils are supported somewhat inside the ceramic, but with enough vibration, these are going to move around a little bit and cause a little bit of work hardening, which puts, a little bit of strain in that wire, and that changes the resistance.
And Bill, what's the size of those little coils?
Well, the wire is 7/10,000ths, and I think the diameter after they coil them is like maybe 10,000ths. Might be 15. I don't recall. It kind of varies depending on the style of element that's being built. Like some of the single elements, they can be a little bit larger. A secondary standard probe would use a larger wire and therefore a larger coil, and also a larger mandrel, because it's a little easier to build something that is very strain-free in a larger version. And with a secondary standard, it's very important to have very much strain-free platinum so you get the best accuracy and repeatability out of it.
So from a manufacturing perspective, just for folks that aren't familiar with RTDs, it's pretty much all done under microscopes with tiny tweezers, and a lot of it is still done by hand. So to give you a sense of what we're talking about size-wise, think more like jeweler's type equipment is what most RTD manufacturing looks like.
And people with very steady hands.
That's right.
So the way these work, it's just it's a resistor made out of platinum wire. The temperature goes up, the resistance goes up, just like any other metal when you run a current through it. And temperature goes down, the resistance goes down. And again, to measure that resistance, we have to run a very small current, usually like 1 or 2 milliamps, real low voltage. And that does cause a little bit of heating in that coil of wire, because anytime you run electricity through a resistor, it's going to heat up just a little bit. So we try to keep the current, everything real low so that we get a good accurate measurement of that resistance. Now the performance of these is defined by a couple of standards, and so all the manufacturers will follow either one or both of these standards. Each RTD has a temperature coefficient, which is just the average change of resistance per degree of temperature change between 0 and 100 degrees C. So that's kind of the basic definition of it. And you can use this little equation down here. But one of the easiest ways that I try to explain this a little bit is like a temperature probe RTD or should say PRT or PT100 that follows either one of the ASTM or the IEC standards. The temperature coefficient is 0.00385. So at 0 degrees C, all of these RTDs are going to read 100 ohms. And at 100 degrees C, it'll read 138.5 ohms. And that's kind of the easy way to look at the definition of that temperature coefficient. And if we had other temperature coefficients, like for example this old US standard, which is pretty much obsolete now, this one at 100 degrees C would read 139.02 ohms, and this JIS spec would be 139.16. The temperature standard, whether it's a secondary standard or a primary standard, usually is made with pure strain-free platinum wire, and that temperature coefficient is a little bit higher. So at 100 degrees C, this would be 139.25 ohms. So just an easy way to look at that temperature coefficient, and also helps explain why it's really important that you know what temperature coefficient your controller, chart recorder, whatever it might be, needs to give you an accurate measurement. If we were to take a replace a probe that was the 3916 and we put in a 385, it's going to end up at 100 degrees C. You're going to be 1.7 degrees C low because that controller is going to be looking for 139.16 ohms, and it's going to tell you it's 100, and if it's only 138.5, we're just a little bit short, so it's going to be reading that much too low. Again, all of these PT100s are going to be accurate at 0 degrees C, but as you go above or below 0 degrees C, that error is going to keep getting bigger and bigger and bigger as you go away from 0 degrees C. One of the other parameters that is used in the manufacturer is called interchangeability. Unfortunately, I see a lot of confusion over this, and some people look at it as accuracy, and it really isn't. It's the tolerance band that the probe manufacturers use to trim that sensing element resistance and get it as close as they possibly can to 100 ohms at 0 degrees C. And the standards define these as Class A and Class B, or Grade A or Grade B. So if we look at this graph, right here at 0 degrees C, this would be the ideal point. Right in the center there is where we want to be. And as you can see, these two standards, as we go up in temperature here, this tolerance band gets wider, and the ASTM spec is just a little bit tighter than the IEC spec. And again, as we go below 0, again, that band widens out. So we can use a graph like this to kind of estimate what the error, what the interchangeability is at any given temperature as we go up or down. Or there are equations that can be used, and these will give you the interchangeability at any given temperature. So if we take our temperature of interest in degrees C, and if it's a negative temperature, just drop the negative sign. We're just going to use the absolute value of that temperature. Plug it into the equation. So if we have a temperature probe that's let's just pick on the IEC, the Class B. It's probably the most common one. Plug in your temperature here, and this will give you like plus or minus, I think it's about 0.35, whatever degrees, and right at 0. And this works for any temperature. And again, it's just the manufacturing interchangeability, or the tolerance band that the manufacturers try to keep that resistance at 0 degrees C adjusted within that band. Most of that control over that is done at the sensing element construction stage. So we put those little coils of wire inside the ceramic mandrel and hook a couple of those coils together while monitoring the resistance. And then the length of those wires can be changed just by either clipping off a little extra or adding a little bit more to get that resistance with as tight as we possibly can. And that's really the only difference between a Class A, B, and C, or even the Class AA. It's just how careful that resistance was adjusted when the sensor was made. Everything else about the performance of that sensing element is going to be the same. And performance is can be very important here, and just it translates to a huge money savings quite quickly. And this little example uses maybe some sort of unrealistic numbers, like the 2.9 cents per kilowatt hour for electricity to heat water, but it's just to kind of show that, if you're off by just 1 degree Fahrenheit, in a process where we're heating water from, room temp up to 100 degrees, it doesn't make much sense to buy a really cheap temperature probe to be measuring that when, you could easily blow almost $1,000 a year in excess energy, or if you're not heating it up enough, it could affect your product quality. So some of the advantages, disadvantages of RTDs, one of the biggest ones is that they're very accurate, very stable. They do have a fairly wide temperature range, typically minus 200 to plus 500 C, and you'll see some of these will go up to about 650 C in an industrial type configuration. There are some issues with those. They tend to have a little higher drift rate, but mostly you'll see minus 200 to plus 500 C. With the PT100 or RTD, you can take those back to a lab and calibrate them and bring them back, stick them in the system, and it's a very accurate, very repeatable, easy thing to do. Some of the drawbacks, response time is going to be slower than a thermocouple. Durability can be an issue in processes that have a lot of vibration. They can only be made so small. If you get much smaller than about an 80 thousandths diameter probe, the lead wires and things that need to be used can be fairly fragile, and so they're really get to be pretty limited use for the really small stuff. And the initial price can be fairly high, but as you can see, if you can use an RTD to get and take advantage of its high accuracy, repeatability, and long-term stability, you're going to save that initial price many times over the life of that sensor. And then identification, and I think we want to do more questions right now.
Yeah, Bill, a couple questions that came in. What's the physical process difference between an RTD and a thermistor? At first glance, they appear to be near identical. So what's kind of the difference between an RTD and a thermistor again?
Well, a thermistor is it's just a I guess I'm not quite sure how to describe it. It's just a solid-state device, and it can be made with a very high resistance. Some of these will have like 10,000 ohms at 0 degrees. The RTD uses wire, typically, like we said earlier, platinum, nickel, copper, and it just measures the resistance of that, whereas the thermistor, and I don't know the exact technicalities of the thermistor and how it works. Other than that, it's just they can be a really rugged design. It just doesn't use any wires or anything. It's just that little solid state device, and I'm sure there's just a little quick Google search would probably tell us exactly what's in there and how it works. Or if anybody else is out there listening in and knows something about that, throw a little note on the Q&A box if you could, and we can maybe get that question answered a little better than what I can do here.
And I think there is also a, correct me if I'm wrong, Bill, but I think there's a inverse temperature relationship with RTDs and thermistors also.
Yeah, the thermistor, you can actually have it decrease in resistance as the temperature goes up, which I suppose are some applications that may be useful.
All right, a couple other questions. Do RTDs and thermocouples normally creep or drift one direction over another? In other words, do they normally creep up or creep down?
Yeah, that's a good question. Thermocouples will generally go up as especially at high temperatures. You're going to see some drift, and it's caused by contaminants getting into the wires, and just how the wires age over time. An RTD can go either up or down. Typically, if you see a decrease in resistance at a given temperature, it's because moisture has gotten inside the probe and caused shunting between those coils of platinum wire, or between the traces on a thin film element, or even the internal lead wires of the probe. And it gives the electricity an easier path to take, so less resistance than it does having to travel through the platinum wire. On the other hand, it can also go up, and that would typically be caused by high vibration or shock, and that work hardens the platinum wire, which increases its resistance, and so you're going to see a higher than actual temperature indicated. So PRTs, PT100, RTD, they can go up or down. And it's kind of a 50-50 mix of what I see. So I guess, is there anything else right now?
Yeah. So we had somebody do a quick Wikipedia search. William, thank you for that. So as Bill said, essentially an RTD is a metal-based temperature detector, and a thermistor is a resistor-based. That being is made out of ceramic, polymer, etc. In order to think of a resistor in your radio, so to speak, something along those lines. So one's more electronic version, if you will. The other is wire-based. Let's see. Something else here. Also, significant difference in the temperature range. Thermistors are much more limited. I think Bill mentioned that as well, as the temperature range.
They're usually, I think 240 Fahrenheit at kind of the top end.
So normally out in industry or out in the world, where you'll see thermistors is going to be measuring air temperature or fairly small differences in temperature. So anything typically related to an automobile, if you're getting a temperature reading on your thermometer in your car or your truck, that's usually a thermistor doing that. You'll have a lot of thermistors actually, on the engine or in the, measuring your cabin temperature, those types of things. They're very small, inexpensive, but much more limited range. Once you actually get into process industry, if you're actually making a product, cleaning a product, sterilizing a product, those types of things, it tends to be much more RTD or thermocouple based. That's kind of the way that the technology has developed over time.
Okay, so I want to get into identification here. We do get a lot of questions about, I've got this temperature probe and the thing, and I pulled it out. It's not working anymore, and I'm not sure if it's an RTD or a thermocouple or what it might be. So I put together a few pictures and things here on some ways to easily help identify some of these devices. First off, with the RTDs, these are typically going to have either 3, 4, or maybe in the case of a dual sensing element, it might have 6 wires on it. And the color codes are going to typically be, 2 of them are going to be the same, whether it's, like we show here, 2 reds and a white, or maybe 2 whites and a red, or the IEC standard colors are a little bit different than what we show here, and I think I've got those right here. We can see they use yellow on some of the dual sensing elements. We don't see that much in the U.S. These will be, we use red and white and green. Let me go back one slide here. We can see that there's two greens and a black. That's you'll see that in the U.S. quite a bit. And the other sensing element would be these two reds and the white. And the reason that we do these are done this way is for lead wire compensation. So the instrument that these are connected to will actually do a measurement of, like in the case of a 3-wire system here, it'll measure this loop of red wire and subtract that from what it measures between this white lead and one of the reds. And then it ends up with just the resistance of the platinum resistor. And that's a kind of a real simplistic way of looking at the way that the electronics work, but that's essentially kind of the end result of what happens. A 4-wire system does the same thing, only it does a much better job of it. It'll completely eliminate any oddball resistance you may have in any of these 4 leads. The 3-wire system depends on all 3 leads each having the same resistance in them. And of course, in the real world, that doesn't happen. So there's always a little bit of an error involved in a 3-wire system. The 4-wire system eliminates all of the lead wire error. So electrical tests that we can do is to take that unknown probe, stick it in an ice bath, and measure the resistance. And if it's 100 ohms, you know, with either one of those tolerance, then we kind of know which class or interchangeability grade it is. And if you're out in the field, don't have an ice bath, typically at room temperature, these things are going to measure about 108 ohms, 109, somewhere in there. And if you measure these 2 red leads, they're most of the time they're going to be like less than an ohm. And then measuring between the white and one of the reds right at room temp, you're going to get about 108 or 109 ohms. And that's right around, 70, 72 degrees Fahrenheit. Thermocouples. One of the easiest ways, if the lead wires have the color code on them, that's the easiest way to tell. Some of these, like this one here, there's just like a purple stripe on one of the wires, and that would indicate that it's a type E. The type T are going to be blue and red, and the type K is going to be yellow and red, and the type J, which I don't show here, is going to be, one lead would be white and the other is red. Now, if you have one of the platinum rhodium thermocouples, this particular manufacturer labels, and they just got like a plus minus thing on here to kind of tell you which lead is which, because there's really not a good way to color code them or to tell which is which, because platinum and platinum rhodium look identical when you just take a glance at them. The platinum rhodium one would be just a slightly bit stiffer than the pure platinum one. And this is the ASTM color coding. There's also an IEC standard, which is a little bit different. The only one I didn't show on there was this type N, which is used more and more frequently. So it's going to be orange and red rather than the type K, which is real similar to it, which is yellow and red. So here's the IEC, and on these the negative lead's always white, and then the plus leads go from black, green, brown, purple, and pink for these various base metal type thermocouples. The other piece of the thermocouple to identify is whether it's that grounded or ungrounded junction that we talked about earlier. Real simple continuity check between the lead wires and the probe sheath. If you get continuity, it's a grounded junction. If you don't, it's an ungrounded junction. Probably a good idea too, just to measure the resistance between the two lead wires too, just to make sure you do have continuity and that the probe didn't actually fail, or that these wires didn't break internally. So that covers kind of the electrical description. I just want to look at a little bit of physical description, something that you can, if you're trying to get a replacement part, these are some of the things that you could get a hold of the manufacturer and at least help them identify just what it is that you have and get a good accurate replacement. Probes that are used in thermal wells will have some kind of spring loading associated with them. The first here, the spring is enclosed in this hex threaded fitting, and the probe will retract into this fitting probably about 3/4 or maybe a full inch. Some of the probes will have just a spring on the outside with a little snap ring stop on it. A European style will have the terminal block attached directly to the probe, and the spring loadings handled by these little spring-loaded screws, so they would be mounted into a connection head and provide the spring loading and keep the probe firmly bottomed out in the thermal well. And then there's a bayonet connection. These are typically used in maybe injection molding machines, where you might have a little well or just a hole drilled into a piece of machinery. It might be a pillow block for a bearing too. And this will just lock onto an adapter that's screwed into that device. Direct immersion styles, these do not use a thermal well. Again, very similar adapter to the spring-loaded, but it's not going to retract into the sensor. It's just going to be welded solid. And then the hygienic ferrules used in sanitary type applications. Also the O-ring style, or the Ingold trade name. And then a compression fitting on a handheld style probe can be used to seal that into a process. And then there's also serial numbers and heat numbers and things that get stamped onto the probe. And this can vary quite a bit depending on the real estate that's available to put a serial number on. It might be stamped onto the hex, a wrench hex, for example, or it might be electro-etched, it might be laser marked somewhere. There'll be serial numbers. I think there's an example here of some heat numbers, which would be for the wetted surfaces. This must be like a sanitary style part where you need that material traceability. And they can be, a lot of these will start out and they might have like a HT prefix, not to be confused with the serial number, but gathering all that information off the probe will help identify a replacement. So just to kind of go through this again, we can look at the lead wires, with an RTD. 3, 4, sometimes 6 wires are pretty common. 2-wire RTDs are not very common, especially used in industry. They can be used in HVAC applications, for building room temperature and things. Thermocouples are just going to have the 2 leads. If it's a dual element, there are going to be 4 leads coming out. Sometimes if you measure continuity on those, they may be all, especially if it's a grounded junction, they may all be connected and welded into the probe tip. If they're isolated, you should be able to electrically identify each of those pairs separately. color codes on RTDs and thermocouples can help identify which type it is. Doing a resistance check on RTDs, also thermocouple, it'd be real easy to tell between a 2-wire RTD and a 2-wire thermocouple, because we're going to have 109 ohms at room temperature versus maybe 1 ohm at room temperature in a thermocouple. And a continuity check on a thermocouple to see whether it's grounded or ungrounded. And also with thermocouples, like a type J, for example, one of the leads is going to be iron, and it's going to be very magnetic. On some of the other thermocouples, one lead is going to be just slightly magnetic. RTDs, on the other hand, they're usually like a nickel or a silver-plated copper wire, and they're not magnetic at all. And I guess I wanted to leave you today with some terminology. Some of the things that you will run into specifying RTDs. You may see ITS 90, which is the newest temperature scale, and then the IPTS 68. Also run into this fairly frequently too, in that there are what you will hear called CVD coefficients, or calendar Van Dusen coefficients. And those are what would be used when you're trying to match an RTD to a transmitter, for example, or some controllers and chart recorders and other peripheral devices. You'll be able to take these calibration coefficients, which are the calendar Van Dusen, or CVD, and plug those into your instrument. And that way it will match the exact resistance temperature characteristics of the probe to the peripheral, and you get a lot better accuracy that way, because it takes that interchangeability number that the manufacturers have to meet, takes that out of the equation almost completely. Some of the laboratory instruments do the same thing, only they use the ITS 90 coefficients, which are a little more accurate. Really, that's about the only difference, is just you get a little better accuracy with the ITS 90 versus the 68. The electronics have a much easier time using the 68 calendar Van Dusen coefficients than they do the ITS 90. So that's why you see that mostly in industrial grade transmitters, controllers, chart recorders, things like that. The triple point of water, it's 0.01 degrees C, and it's where water exists at a liquid, solid, and a vapor all at the same temperature, which is not too many other materials do that. And water is very unique in that way. And it's a good fixed point for calibrating like a temperature standard, whether it's a secondary or a primary temperature standard. Not much use for industrial style stuff, because you really don't need that kind of accuracy when you're trying to calibrate that type of sensor. And then the R0 term, which is the resistance at 0 degrees C of a PRT or PT100. And I see I did not put PT100 on here, probably should have. Also SPRT, which is the standard platinum resistance thermometer, and that's what would be used for calibrating other PRTs or PT100s. And insulation resistance, another commonly seen spec for RTDs. And that's really about kind of the most common ones that you're going to run into. Kind of pick your favorite off the list, and I think that is going to just about wrap it up, and then we can maybe do some more questions.
Yeah, so just if anybody has any questions, do go ahead and type them into the chat box or the Q&A section, and we'll go ahead and see if we can't get you an answer. While we're waiting for that, just to let folks know there is how to choose a temperature sensor for your application will be our next RTDology event coming up in February. So look forward to seeing you at that event. You can go on our website and register for it right now. Otherwise, we will be sending out reminder emails in the coming months. So. With that, just another reminder, this session is being recorded, and it will be posted to our YouTube channel shortly. That's usually up within a day or two, and we can go ahead and send a email link to that as soon as it's up. So we'll go ahead and get you that. So a couple questions. One was discuss thermocouples and multi-junction setup to increase millivolt differentially for small temperature difference measurements. Does that make sense?
Scroll back on that one a little
I know,
bit.
unfortunately, yeah.
I guess I'm not 100% sure what that's referring to. I know there are cases where we can take and do like an average temperature measurement with thermocouples by using what's called a swamping box, and we'll just bring a bunch of thermocouples in. That can be done either in like a serial connection or done in parallel. But I'm not real familiar with doing that to measure small temperature differences.
So maybe Gregory, if you're still on the line, and if you've got any additional information you could give us, go ahead and type that in. We'll see if we can't get you an answer, or we can address it offline as well.
I could do a little bit of research on that too afterwards here, and maybe just shoot you a quick email because I guess I'm not 100% sure maybe what we're looking for there.
Another question, how can I incorporate a control chart of my, can you read that?
Yeah, it's the resistance at triple point of water. Let's see. Yeah, that's another good question, and I'm not 100% sure how to answer that other than, I know what we do in our lab is that we'll measure our standard PRTs every day before they're used to do comparison calibrations of other probes. And so we track that information, and if it starts to change by, I think it's 3 millikelvin, then we kind of raise a red flag and say that one has gone out of its tolerance, out of its tolerance band, and it will no longer maintain our published calibration uncertainties, and then that goes outside of our accreditation. And so we do keep track of that, and just to see if there's any kind of a trend happening. And I think that's what you may be referring to there. If that's I'm not sure how else to answer that right now.
Okay, and again, I don't know. Next, do we have contact information on the next slide, Bill, or maybe go back to the previous slide? Did you have your
I don't.
Info up there? Okay.
Probably the easiest way is to shoot it to info@burnsengineering.com, and that way it gets to the whole applications group, and we can get you an answer pretty quick that way.
Yeah, if you ever have any questions on temperature, whether it's a Burns product or not, you're just looking for some assistance, feel free to go ahead and email us at info@burnsengineering.com, we'll work to try to get you an answer. We do a lot of that. The more folks know about temperature, the better measurements that they're going to get. So that's just a service we provide. So. It does look like we have another question. On one of our specifications, it has a 0.03 degrees C as the max deviation of nominal characteristics. Others have a 0.3 degree C for this value. What does this value mean? Maximum deviation.
My guess is that they're looking at, whatever the calibration point is, they don't want it to differ more than that 0.3 degrees C. Typically, it'd be like a plus or minus number, though, and it's a little bit suspicious in that it's 0.03 and 0.3. It almost seems like there might be a typo going on there. 0.03 would be really tight for like an industrial grade PRT. 0.3 would be pretty realistic. So I guess I'd have to, probably have a little more information on that run to really, get the best answer out of that. But it looks to me like they maybe misplaced the decimal point, unless it's for a temperature standard of some kind. Aha. We have more information.
Yes. Here it is.
High accuracy RT. Yeah, well then the 0.03 might be pretty realistic. Our calibration uncertainty for an industrial grade probe is 0.025 degrees C or 25 millikelvin. And depending on how it was being measured, that 0.03 number could be pretty realistic. I would think it would have to say plus or minus, though. So.
Okay. Yeah. If you do have any more questions on anything on this one, Mark, if you've got more that you'd like some information, just go ahead and send it to info@burnsengineering.com, and give us your phone number, and somebody can give you a call and walk you through and try to get you the answers that you're looking for. So with that brings us to the end of our session. I want to thank everybody very much for joining us. Hope to see you at our next session, and have a good afternoon.